But I think, again, in the UK, the real growth area we have is for shallow geothermal for heating and cooling. So one of the great things about the UK is that we have lots of really good quality aquifers that we've been exploiting for a long time for groundwater usage. So the chalk aquifer in the southeast, the Sherwood sandstone in parts of the Midlands and the north, and so on and so forth. There are carboniferous sandstones in Scotland. And we know lots about these aquifers because we've been producing groundwater from them for hundreds of years. So we have a really quite extensive borehole database with the BGS, so you can look at characterising the aquifer properties and how how groundwater will flow through them. So we have a lot of good aquifers shown here in green, and even though we don't have good aquifers, we can still use closed loop boreholes for geothermal. And often those aquifers are co-located with areas of high heating and cooling demand in the UK. And I must emphasise, I think cooling is going to become more and more important as we move through the next decades. It can be very dangerous. We have deaths in summer when we have very high temperatures. People can't control the temperature in their own home. So I think we should be looking to offer cooling as well as heating if we can through these low carbon geothermal technologies. And in fact, London is the city in the world with the highest rate of increase in demand of cooling at the moment. It's really going up very quickly. So in fact, in London, we have already around 70 large-scale geothermal systems operating, primarily using the chalk aquifer for open-loop systems and a small number of closed-loop systems. I'm sorry, that map is just useless, isn't it? I mean, you can't make anything out on there. But the green blobs are active open-loop systems, and they're mostly concentrated around about central London, which is sort of obscured here in the middle of the map. So it's not like we're not doing shallow geothermal in the UK, but there's a lot of potential to grow it a lot more than we have at the moment. So about 70 systems operating in London, and then a handful really operating outside of London, very specific buildings, and there's one or two in Manchester and so on. But again, a lot of potential for growth. So this is something we've been looking at, and in fact we've been engaging with DESNZ to look at solutions for low carbon heating and cooling. It's also, heating and cooling is one of the most difficult sectors to decarbonise, okay, because we're looking at trying to replace millions of gas boilers and so forth in individual properties. So in fact it's much harder to decarbonise than electricity. Electricity, great, we've got wind, we've got solar and so on, but heating and cooling is really tough. So we've been looking at how much electricity you need for heating and cooling. This is air source heat pumps, so kind of being pushed very heavily at the moment because they're very easy to install. This is traditional groundwater heating and cooling, so there's open loop. This is our ATIS system where we store and reuse heat and cool. And basically what you can see is we need to use less electricity for ATIS than for any of the others. And that's because we don't need to make the heat pump work as hard. And in fact, for cooling, we don't need a heat pump at all. So that's good for two reasons. One is that it actually puts less demand on the grid. So one of the big problems we have of rolling out heat pump technologies, along with electric cars and all the rest of it, is that National Grid ESO are really struggling now with the extra demand they're going to have to supply in terms of electricity. So it means upgrading lots and lots of grid connections and so forth as everyone starts to put these technologies in their home. The other big thing, of course, is it comes with lower carbon emissions. So the less electricity used, the lower the carbon emissions are going to be. And I'm not going to talk through this graph in detail. The main take-home message is that, you know, this storage technology, aquifer thermal energy storage, it delivers heating and cooling with lower electricity demand and also lower CO2 emissions than conventional open-loop geothermal. It's efficient for heating because we deliver warmer water to the heat pump. I've done my job. And it's very efficient for cooling because we can just directly cool the buildings without using the heat pump at all. So we've actually been looking at, okay, so, you know, is this a big deal, right? So, you know, we've said that internationally, geothermal supplies 3.5% of heating and cooling demand. If it's going to be the same in the UK, then clearly DESNZ should be looking at something else as a solution for the UK's heating and cooling demand. So we've done some kind of probabilistic modelling using Monte Carlo methods, which again will be familiar to many of you who come from the oil and gas industry. So we don't really know a lot of the numbers exactly, but we can look at a range of them and then make lots of forward predictions and come out with some probability distributions. So the first thing we can do, and again I won't go through this in detail, is we can look at how much energy we think these systems can supply per unit area. And then we can look at what the demand is across the UK, and then we can match those two things together to look at how much of UK demand could be supplied. And it turns out that we could meet about 60% of the UK's heating demand and about 80% of the UK's cooling demand if we had a really widespread rollout of these particularly aquifer thermal energy storage technology. So it could be a massive deal in the UK. This is not 3.5%, it's a very big percentage of what we need. And we do actually have some operating systems, so we can demonstrate that it works in the UK context. We have 11 systems altogether, so not many. 10 of them in the chalk and 1 in the Permo-Triassic Sherwood sandstone in Manchester. And the kind of scales that we have for this is the 11 systems. They typically use 2 to 8 boreholes, but they offer sort of megawatts of heating. So the biggest ones here in London, Riverside Quarter and St James Riverlight, these are 2 megawatt heating and cooling systems. This is not individual houses. And in fact, this is a picture of one of the developments that's supplied by an ATOS system in Wandsworth in London. This is a big development. There's 500 flats and shops and so forth. And this is being supplied by an 8-well ATOS system with significant CO2 savings over conventional CHP plants and so forth. So we have got demonstrators that we can take to the government and say, it works, we can show you that, and we can roll it out much more broadly. There's some things we need to think about though, okay? And one of them is that the chalk is a very complex aquifer. So what we see, if we sort of look at the stratigraphy, we've got the London clay in London, and then we've often got the chalk, and often we get some sands that sit just above the chalk, the Thanet sands and the Woolwich beds and so forth. And at the top of the chalk, in lots and lots of boreholes in London, we see huge amounts of flow. Right at the top of the chalk, just below whatever sits above it, the Thanet sands or the London clay or whatever. So we run flow logs through these wells, we see massive amounts of flow coming into the chalk. And we think this is essentially a karst, okay? So the chalk has been exposed, it's been eroded, and we can go and look at outcrops. So this is a quarry down near Sutton, I think it is. And we went down and had a look at it to show our students kind of what the chalk looks like. And in fact, if you look at the top of the cliff, you can see lots of kind of vertical features in here. And this is a karst horizon, and in terms of flow, it's like having a cave system, and so you get huge amounts of groundwater moving through the karst. When we come to look at storage and how an ATOS system will operate in London, this is really important because it affects a lot where the plumes are going to go. So in a nice Dutch system, the plumes form cylinders around the wells. But because we have all of this massive flow unit, this karst at the top of the chalk, this might be where the laptop doesn't manage to do the, yeah, this should be a video, and I don't think it's going to play. No, it's not going to. Oh, that's a shame. Well, anyway, what you would have seen is instead of nice cylindrical plumes, they're like pancakes. They come right out and they spread right along that karst horizon at the top, which means they can interfere with each other, which you don't want. If you bring warm water and cold water together, they mix and you destroy the value of storing the heat and the cool. So one of the things we're looking at is how we might engineer these systems differently in the chalk to avoid that problem. So maybe make the plumes offset vertically rather than horizontally, for example. And we also need to look at things like mixing groundwater of different compositions. So in lots of boreholes in the UK, this is not from the chalk now, this is from the Sherwood sandstone. You often see the water becomes quite saline as you go deeper. So this is plotting chloride concentrations, nice and fresh, it's been refreshed by meteoric water, and then you can move into something which is much more kind of connate, and it's much more saline. But alas, you're not going to see that, I don't think, because I don't think this movie is going to play either. But if it had played, you've seen the salt water being sucked up into the well and then puffed out, because remember, these are bidirectional wells. So what you bring into one well gets injected into the other. So it sucks up the salt and then puffs it out, and then sucks up the salt and puffs it out. And you can start to mix up salt water and fresh water. And we don't want to do that because we don't want to contaminate nearby freshwater groundwater supplies. So there's lots of potential, but we have to be aware of what's happening in the subsurface and how we engineer that responsibly to make these systems sustainable and economic and environmentally friendly. Oh, it works. There we go. I didn't expect that. There we are. You see the salt. So this is the potable water drinking limit for salt. This is very salty water down here, and you can see it's being moved up, and we're starting to redistribute salt into the aquifer, which is not great. So we want to engineer these systems so they don't do that. So I think generally overall prospects for geothermal in terms of electricity generation, fantastic where you've got the hot rocks and the fluids. So fantastic where you have these hydrothermal systems associated with volcanism. We're still struggling to extend it beyond that into deep rocks which are hot but dry. In terms of shallow geothermal, it offers baseline low carbon heating and cooling. I think it has real potential for very widespread uptake around the world and in the UK specifically, but we need to be responsible about how we understand the response of the subsurface. So